Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, we are going to apply the method of transformations to find the probability distribution of a function of a random variable. Let's begin. So, the example that I would like to solve with you is this one. This is the problem that would like to solve in this video. We have an original random variable v, right? Okay, and then the PDF for that random variable v is given by a times v squared e to the negative b times v squared for positive v. Okay, and it's going to be 0 otherwise. So this is the non-zero part of the PDF of the random variable v. Okay, and b is also some constant, right? Anyway, the our task, the goal, is finding the probability distribution of a function of that random variable v, which is given by m times v squared divided by 2. Okay? Well, since we want to apply the method of transformations, let's try and remember what we have to take into account, because if you recall from another video where we mentioned this method of transformations and its relationship with the method of distribution functions, right, what we said is that the method of transformations, it's a particular case of the method of distribution functions. But in order to apply this method, the method of transformations, we have to check that an important condition holds, right? So let me remind you what that condition is. So here's the summary of the transformation method. So what we have here is a function of a random variable v, right? And this is the condition that we have to make sure is satisfied, that this function h of v is either increasing or decreasing. Okay, why is that important? Because if that function is either increasing or decreasing, that guarantees that the inverse exists. Okay? And this condition must be checked for the values v, where, well, it should be, yeah, for the values v where the PDF is non-zero. Okay? Okay? Here we go. And this is the for the PDF of the random variable v. Okay? Here we go. Let's check that condition. So we have this random variable, right? It's f of v. It's given by this over this region, the v's that are positive. Okay? So when we see the transformation, first we have to see where these values are going to be mapped out. Okay? So if we apply this transformation for v's that are positive, right, what we have is that mv squared divided by 2, oh, that's going to be positive, right? So these w's, right, the new random variable will create w's that are positive, okay? And they will be the PDF that we're going to have is the support of the random variable w will be for w's that are greater than 0. We are going to have this, and 0 otherwise, okay? So let's check that condition that we were mentioning. So v is greater than 0. Let's make a graph. Let's create a sequence of numbers. Say it's greater than 0, right? So something that is greater than 0 up to, say, I don't know, 100, right? And the distance between each of those guys, let's set it equal to 0.001. And now let's create something that looks like w. We don't have the value of the constant m, right? So let me set it equal to 1, right? So what we have here is that w will be v squared divided by 2. And let me plot that function on the first. I'm going to have the values that go on the horizontal, then the ones that go on the vertical. Then type, I want a line, so I'm going to be using an L. I want it to be dashed. I want that guy to be blue. See if that works. Okay. And it makes sense, right? Okay. Yeah, I mean, v square, it's going to look like a parabola, right? But we only have the positive part, right? And that's important. If we were applying this transformation, that function mv squared divided by 2, to all numbers between negative infinity and infinity, then we would be in trouble. Why? Because in that case we wouldn't have an increasing function or a decreasing function, and then we wouldn't be able to apply the transformation method. But in this case, since we're only interested in v's that are positive, and that's where we have the non-zero part of the PDF of the original random variable v, then over that region we have that this function, the one defined by our transformation, is increasing, strictly increasing. Then the inverse is going to exist. Then we get to apply the transformation method. Make sense? So that's the condition that you have to make sure is satisfied, that you check that for the non-zero part of your original PDF, you have either this function h is either increasing or decreasing. Okay, so once we have checked, and in this case we already have a graphical representation of that transformation, it's increasing, right? So checked, since it's increasing, we're going to be able to find the inverse. Step number 2, we have to find the derivative of the inverse. Step number 3, we will find the PDF of w like this. We evaluate the PDF of the original random variable, in this case v, at the inverse, and then we multiply by the absolute value of this derivative we found on the previous step. Make sense? Okay, so let's do that. Let's do step 1. Find the inverse. So step 1. So we have, right, the transformation is W equals mv squared divided by 2. W equals mv squared divided by 2. mv squared divided by 2. So we multiply on both sides by 2, right? Then we end up with just mv squared. We divide by m on both sides. Oops, not what I want. Well, it works. We divide by m on both sides, and then finally we take the square root on both sides, and since v is positive, right, when we take the square root we have to consider only the positive root. Okay, so it's a one-to-one function. We were able to find the inverse transformation, right? This guy is H inverse, okay, the one that we have here, right? Okay, now step number 2, let's find the derivative. Okay, here we go. Before we do that, just let me re-express this like that. Let me rewrite this guy as 2w divided by m to the power 1/2. Okay, that's the same as the square root of 2w divided by m, right? So step 2, let's find the derivative of this guy, right, with respect to w. So derivative of v with respect to w, derivative of v with respect to w, right, it's going to be just 1/2 times this guy to the power 1/2 minus 1, which is going to be just minus 1/2, right, times the derivative, right, we have to apply the chain rule of this with respect to w, which is going to be just 2 divided by m, right? So let me write that down here, 2 divided by m. Okay, making progress. So that's basically step 2. But it would be a good idea, and to simplify that as much as possible. So let's do a little bit of algebra here. So first, note that 2 times w divided by m to the power minus 1/2 is the same as this. First, the minus 1/2 is just saying that what we want is the reciprocal, right? And then we want the square root of the reciprocal. Okay, so what we have here is m divided by 2w, and we have that to the power of 1/2, which is just the square root. Okay, so let me just rewrite it here like this. We have 1/2. We have then this guy here, and let me take the square root of m and the square root of this guy too, and then we have this, right? Okay, now note that these two guys, these 2's, will cancel out, so let me get rid of those guys. So we have a 1 here, right? And then that m is the same as the square root of m times the square root of m, so one of them is going to cancel out, and then we're going to end up with just 1 over the square root of 2w times the square root of m, which we can rewrite just like this. 1 over 2w times m, the square root of all that product. Make sense? Okay, so now we have step 2, and we have simplified that expression. That is going to be helpful in the near future. So step number 3, we want to evaluate this. Okay, so let's write that down as a reminder of what we want to do here. Step number 3. So the PDF of our new random variable w will be given by evaluate the PDF of v at the inverse, and then times the derivative that we found here on step 2. Okay, here we go. So let me go back to our lecture notes here. So this is f evaluated at v, right? But we're going to be evaluating that at different point. The inverse is here. And this guy, remember, this is just the same as this, right? Well, maybe I should rewrite it. Let me get rid of those brackets, and let me rewrite it just like this. Okay, so that's the inverse, right? So let's evaluate our function there. Okay, it's going to be the old PDF, one for v, evaluated here, square root of 2w divided by m. Let me substitute there, times the absolute value of that derivative. Okay, make sense? Okay, so let's find it. So we said is a times, if you evaluate at v, is a times v squared e to the negative b times v squared. Okay, so what we're going to end up with is a times whatever square, so it's going to be just a times this, right? Makes sense? Times 2 times w divided by m, makes sense? E to the power negative b times v square, which is again this guy here, right? So let me copy paste this guy. Well, let me write it down here. 2w divided by m, that would be v squared, okay, times this, the absolute value of the derivative from step 2. Okay, so now let's just do a little bit of algebra, okay? So first let's deal with these guys here, right? So that, let me rewrite that constant like this. Let me place that 2 outside, right? So 2. Let me rewrite w as the square root of w times the square root of w. And that m, let's leave that guy as is, okay? This guy here, I'm going to leave it alone for the time being. And then yeah, just let me copy paste this guy here. So note that what we're going to have here is that 2, we can also write that guy down like this, the square root of 2 times the square root of 2. So, and this guy here is the same as the square root of 2 times square root of w times square root of m. So this guy will cancel out with this guy. We're going to end up with one of these guys canceling out with this guy, right? Oops. So in the end, what we're going to have here is, let me copy paste some of them and get rid of some of them as well. Yeah, we're not going to need those guys there, okay? Because this guy, square root of 2 will cancel out with this guy, square root of w will cancel out with this one, and this one here is not going to cancel out, but m is the same as m to the power of 1, square root of m is the same as m to the power of 1/2, so let me rewrite that product as m to the power 3 divided by 2. Make sense? Are we good? Yeah? Okay. So now let me re-express what we have there. Okay. It's just that I want that guy in a form that is friendlier and that is going to be easy to recognize, right? So now instead of writing square root of w, how about we write w to the power 1/2? Okay. Okay. Now that one I like. Let's leave this guy. We could, combine these two, then have that as our constant, and then finally let me just use something that we have from the problem. Okay, so note that v equals m times, well, m divided by 2 times k times t. Okay, so using that, since b equals m divided by 2 times kt, right, then what we're going to have is that b times 2w divided by m, right? So b times 2w divided by m is the same as that constant we had there, m divided by 2 times k times t, times this 2w divided by m. Okay, so these two guys cancel out, m and m, that 2 and that 2, they will cancel out as well. So what we end up with is just w divided by 2 times kt. Okay, so w divided by kt. Okay, so let's use that here. So instead of writing minus b times w divided by m, we're just going to be writing minus w divided by kt. Make sense? So minus w divided by, kt. Okay? Now, something important is that what we have found here, right, is the PDF of w for w greater than 0. Okay? And what we're going to have is that f of w will be 0 otherwise, right? Because this guy is going to be 0 otherwise. Okay? But the non-zero part, the interesting part, is this one here, right? So finally, why did I write this guy here? Why did I do all the algebra? Because I want you to be able to quickly recognize what this guy looks like. One last step would be this. One half, w to the power 1/2, is the same as w to the power 3 divided by 2, right, minus 1. Okay? So 3 divided by 2, minus 1. Okay? So now, let me show you our table. You can find it on page 838 of our textbook, right? And the expression for a gamma, right? The PDF of a gamma is some nasty looking constant, right? 1 over the gamma function evaluated at alpha times beta to the alpha power, the variable to the exponent alpha minus 1 e to the negative y, the variable, right, divided by beta. So this is the expression for the PDF of a gamma with parameters alpha and beta. So if you compare this with this, you go, oh, this guy looks like a gamma, right? So the PDF of W looks like a gamma PDF with parameters alpha 3 divided by 2 and beta k times t. Okay? So, if this guy has the hope of being a legit probability distribution, this constant here, right, better be equal to this constant here. Okay? And that's the last comment that we make here. Here on our lecture notes we have kind of a summary of the steps we took. We didn't show all the details here, but it's a summary, right? And then here we reached that point, and then we make that observation. Okay, this guy looks like the PDF of a gamma distribution, but in order to be a legit gamma, this constant would need to be equal to this 1 over the gamma function evaluated at alpha times beta to the alpha power, right? And that's it. Okay? So, bottom line, let's summarize. We had an original random variable v. We were given the PDF over the region where it was different from 0. That PDF will be 0 for negative v's, right? Then a function in terms of v is defined, and we would like to know the distribution of that function, of that transformation. Okay, so to find this, what we did is we applied the method of transformations, but we had to be careful in checking that that function, that new random variable w, could be thought of as a function that had an inverse. And in order to have an inverse, one way of guaranteeing that that function has an inverse is if that function is strictly increasing or strictly decreasing. Okay, and then we just apply the 3 steps of the transformation method. We find the inverse, we find the derivative of that inverse, and then we just since we know from what we did in another video, it's basically an application of the chain rule, we will have to evaluate the PDF of the original random variable at the inverse times the derivative of the inverse with respect to the new variable, right? And that's it. Well, thank you so much for watching. Take care and keep working hard. See you next time. Bye.